Have you ever heard of these divisibility tricks? Like, if the sum of the digits of a number is divisible by 3, then that number is also divisible by 3. Well, here's an explanation of why some of these tricks work using modular arithmetic. First, I must introduce the idea of a modular congruence. When we say that A is congruent to B mod M, where the triple bar is the congruence sign, that means that the remainder of dividing A by M is equal to the remainder of dividing B by M. Here are some examples of congruences on screen. Notice how all these numbers are each apart by their respective modulus, and how the numbers may be negative. Also, that the last congruence is particularly important into finding a divisibility trick for division by 3. Consider a 4-digit number that is divisible by 3, or writing it in congruences, its remainder after division is 0. The number we can write as the sum of multiples of powers of 10. We see that all powers of 10 are 1 in modulo 3, because 10 itself is 1 in modulo 3, and because all powers of 1 are equal. Because we can individually apply the modulo to every term in this sum, we see that if a number is divisible by 3, then the sum of the digits also have to be divisible by 3. And we can trace back our logic in a similar way to see that the converse is also true. Understand that we are not just limited to 4-digit numbers, since any power of 10 has a remainder of 1 in mod 3. Very similarly, we can develop a divisibility trick for 9, since the remainder of division of 10 by 9 is 1. We again expand the number to sum of multiples of powers of 10, and apply the modulo to each term. Now we know that if the sum of the digits of a number is divisible by 3 or 9, then the number is divisible by 3 or 9 respectively. We can develop a slightly more interesting trick for divisibility by 11. Remember that congruences may have negative arguments, so in division by 11, 10 and minus 1 have the same remainder. We can again split the number into its powers of 10 and substitute the negative 1 everywhere the 10 is. Negative 1 to some power will be positive when its exponent is even, and negative when its exponent is odd. So we see that the number is divisible by 11, then the alternating sum of digits is also. Again, we can trace back our logic to prove that the converse is also true.